La, 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 la. All right, excellent. Here we go. Dear Heavenly Father, we thank you for this day. Thank you for these students coming back despite the test. Help us to understand the material today. Help us to, again, Lord, glorify you in what we do. And we just thank you, Lord, for your many blessings to us this day, Lord. In your name I pray. Amen. All right, so let me just spend a minute or two going over the solution of the test. I'm trying out a new thing. Oh, that's not going to work. Wait. Where's pause? Let's turn out the lights. Hey, what? There we go. The department just got a new scanner. I didn't feel like putting in my email right before class, so this is my solution. I'll eventually figure out how to pause this thing. Curses, not in time. All right. Sorry, I'm new to this format. I don't want it to be dark when I pause, you dumb thing. Thanks, Microsoft. Losers. Let's see here. No, I don't want closed captioning. Does this need a button? All right, I guess we'll just have to watch it. So, kinetic energy, yeah. Conserve energy. Solve for L. Conserve momentum, then conserve energy. Well, energy at the start was energy lost anyway. Here is just conserve momentum. Oh no, it was over here. You couldn't use inverse tangent. Ah! Sorry. It may be happier for me than for you. I bet you guys got that. And then here, you just differentiate with respect to x, with respect to y, with respect to z. Gives you this, this, and this. That wasn't a hard problem. Basically, you're stuck between here and here. Whoa. Here and here. Whoa, 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 whoa. Otherwise, you have negative kinetic energy. Yep. And so you got to draw some picture like this. Set up your picture, conserve momentum, conserve energy because it's elastic. And so you square this and then set v naught squared equals. And then you add angles formula and then alpha. Oh, yep. Oh, 9 degrees. Oh, there it is. Okay, so that was like perhaps a ridiculous way to do a test review. Hey, but hopefully now you at least have the answers to the test on the YouTube, right? So I will hopefully have your test graded and back to you by Tuesday. I had hoped I was going to get it done today. It just doesn't happen. All right, so what's next? So I hope that didn't make your head spin because this will certainly go back. I'm about to make math great again. I mean physics great again. Go back up there. Go back to Mexico. or wherever it is that you came from. China. I don't think he has. Does he have anything? No. I don't think he wants to send the Chinese back. I mean, he just wants to keep their money, I think. Yeah. Oh, really? That's because I said something, though, so you know. So rotational physics, we've mostly talked about straight line physics, right, in 1 or 2 or 3. Why are there fruit flies in here? Not cool. All right, sorry. We've mostly talked about linear physics in 1 or 2 or 3 dimensions, right? So the next thing we're going to talk about is basically how to study the physics of rotational things. Okay, so there's different parts to this story. So we have to talk about the kinematics of rotations, right? Just the study of motion itself. We have to talk about the study of rotational kinetic energy, right? Like energy conservation for rotational systems. And then, of course, we also get to talk about rotational dynamics, the study of, like, what's the rotational Why is there a bug in here? Sorry, I'm distracted. There's also a rotational analog of force, which is called torque. The rotational analog of mass is called the moment of inertia. Kinetic energy is still kinetic energy, but the kinetic energy, instead of being proportional to 1/2 mv squared, not proportional, equal to 1/2 mv squared, it's actually 1/2 the moment of inertia times the angular velocity squared. So this is where we're going. We want to understand rotational analogs of kinematics, of energy conservation, and finally also of like F equals ma. How's that work out? That's torque and angular acceleration as opposed to linear acceleration. So we'll explain all these things. And we'll also learn about conserving angular momentum as opposed to linear momentum. All right, that's where we're going. To start with, though, I'm just going to start with something really simple, which is just to try to discover what does kinetic energy formula look like in polar coordinates. You guys know what the kinetic energy is. If I've got some mass, right, and it's at the point x comma y, what's its kinetic energy? We could write it this way, right? 1/2 m x dot squared plus y dot squared. Now, maybe I never wrote it that way before, but I could write it that way. See, what is x dot? It's dx dt, okay? And y dot is dy dt. So what's x dot squared plus y dot squared? It's nothing more than dx dt squared plus dy dt squared. Well, you know what that is. That's the square of the speed, right? It's the speed squared. So there is a formula for the kinetic energy in terms of the derivatives of the Cartesian components of the particle. You guys can see that too, right? No? All right. Well, it's not good. You also hear the other people talking, right? No, sorry. Sorry, we shouldn't make light of these things. People have serious problems. I know. Sorry. So what's the deal? What does this formula look like in polar coordinates? How do you relate Cartesian to polar coordinates? How about this? R cosine theta, right? R sine theta. Now here, this R and theta, these R and theta, these, right? These R and theta are functions of what? Time, t, right? So if I differentiate dx dt, what is it? It's, see x dot? It's equal to r dot cosine theta minus r sine theta theta dot by the product rule and the chain rule. Because I'm differentiating with respect to t. And likewise, by the product rule and chain rule, I have y dot is equal to r dot sine theta plus r cosine theta theta dot. What happens then if I square these and add them together? Right? That should give me the formula for kinetic energy in polar coordinates. Right? So let's see here. What's x dot squared? looks like an r dot squared cosine squared theta minus 2 r dot theta dot r cosine theta sine theta. And then one more term from squaring what? Plus r squared sine squared theta dot squared. Yes, sir.
I don't understand why changing x to x dot added that, like changed the r cosine theta.
So what we're doing is we're ddt of r cosine theta, right? That's x. So that's dr dt times cosine theta plus r times ddt of cosine theta. Because both r and theta are functions of time. So this is by notation, that's r dot cosine theta. Now this over here is minus r sine theta. I'm differentiating not with respect to theta, but with respect to time, so I have to multiply by theta, d theta dt. That's the chain rule. You see, but this is exactly what we call theta dot.
So r is the constants of it.
Yes, r and theta are functions of time. We're imagining r and theta are the polar coordinates of this particle that's moving in the plane. Yes, sir?
Is that theta dot being multiplied just by the, like the last term, or by the whole thing?
This theta dot
Yes.
just multiplies the last term only. Yeah. There is just an r dot or a theta dot on every term in x dot and y dot. Now, what's y dot squared? Uh-oh. So it's almost the same formula, right? It's just in the middle, the cross term has got a plus instead of a minus, right? And you've got a sine squared where you had a cosine squared, and you've got a cosine squared where you had a sine squared. But that's really good news. What happens when we add these equations? Everything cancels, except the stuff that doesn't cancel. It seems somewhat tautological. Let's see here. X dot squared plus y dot squared is equal to r dot squared plus r squared theta dot squared. Let me try to draw a picture to better explain the meaning of what's going on here, guys. So, so here's my particle out here, m, right? And so you've got two things, right? It's radial distance, that's supposed to be straight line, sorry, and theta measured counterclockwise, right? If you draw the velocity vector of this particle, it looks maybe something like this. I don't know, whatever. Could be a lot of different things, right? There are two pieces to that vector. There's a radial component and then another piece which is perpendicular to the radial component. So the radial component to the velocity, I'll draw in blue, like this. So what you have there is you've got v sub r, r hat, the radial part of the velocity, and then there's also a angular part to the velocity, right? Like this. I would call that v sub theta, theta hat perhaps, or something like that. Now, usually you say v theta. What is v theta? V theta is equal to, and what's VR equal to? I'll write it down here actually. V theta equals to VR equals to what? So let's see here. Let's think about this. If the angle's not changing, right? If theta doesn't change, then you should just get the blue piece, right? Does that make sense? If theta dot is 0, if the angle is constant, then you're just moving in the radial direction. And as you can see, you just get r dot squared, right? So r dot is, this is, I mean, just let me tell you, this is r dot, this is dr dt. Whereas the velocity in the theta direction is r theta dot. Now, or you could write this as r omega, where omega is equal to theta dot. That's a definition, okay? The so-called angular velocity. Excuse me. So if we go back to the question of kinetic energy, what's happened here? If we want to understand the kinetic energy of a particle moving in the plane in terms of its radial and angular motion, what do we have? One half m r dot squared plus r squared theta dot squared, right? By our above calculation, which is what? 1/2 m r dot squared plus 1/2 m r squared theta dot squared. Let me interpret what that formula means, okay? This piece right here, this is the radial kinetic energy. This right here is the rotational kinetic energy. All right. Any questions? All right. So I'm going to change gears just a little bit here. So, to consider the full story here, when the radial distance is changing and when the angle is also changing, that's somewhat complicated, right? I mean, you can do it with calculus, right? Here's the start of the formulas for it. But we're going to focus in on a particular case throughout most of our problems. In most of our problems, what's going to happen is this radial distance isn't going to be changing. Right? So we usually focus in here on problems where you're just studying motion of a rotation. So like the radius isn't changing, the mass is just kind of going the same distance from some central pivot point, and we study the motion of that. That's a rotational. That's a simple rotational motion, and that's mostly what we study in here. So let's focus in on that case. So we'll just say r is equal to capital R just for the most part here. So you've got some pivot point, reference point of rotation. I don't know, what do you want to call it? Origin, how about that? Right, and then you've got some mass out here, whatever, and its angle theta is that, right? And what's it doing? Well, it's going to be doing what? It's going to be going in a circle, right? So if we say compare theta 1 over here to, say, theta 2, then what's the, we would have a certain angle subtended here, right? Change in theta. So like change in theta would be what? Yeah, theta 2 minus theta 1. Now, theta is in radians, okay? All the formulas I'm writing for you guys are going to be in terms of radians. I assumed radians when I differentiated here, right? If theta was in degrees, I'd need all kinds of multipliers because theta is only nice in radians. You know, there are questions here and there we ask about degrees because, well, I don't know about you. Somebody tells me, well, just make me a table where the corners have like, you know, a radian. That's like a radian at each corner. I'm like, what? You know, if they told me I wanted a table where the corners come to like 80 degrees or something, it might be weird, whatever, but at least I'd understand it, you know? I personally I can't directly visualize things in radians personally. I see degrees. All right, so this would be the so-called the arc length subtended. You might say the, I guess you could say change in S. I'm tempted to just write S. A lot of times I write S there. Let me just write S there, if you don't mind. Now, fine, change in S. I'll get over it eventually here. All right, so the change in S is what? What's the relation? So this is R, of course. So we got what? We got R times the change in theta, right? So that's the arc length subtended. You know, this, I mean, a lot of times you'll just see this written more briefly as what? S is equal to R theta. What does that assume? It assumes you're starting from 0, right? And theta, like, that would be a good formula if you're thinking like what? So here's theta, right? Starting from there, this distance is S, right? Think of it that way if you want. What happens if you, and then of course we can differentiate this, right? So what's ds dt? It's r d theta dt, right? What is ds dt though? ds dt is a speed, right? No. I mean, and alternatively you could say, well, ds dt is what? It's the square root, right, of x dot squared plus y dot squared, right? So you could also look at this as being the square root of the stuff we just went through, right, which was r dot squared plus 0, right? 0 because I'm an idiot. Other way around. 0 squared plus r squared theta dot squared, right? Which, by the way, is r theta dot. Assuming theta dot's positive, of course, but I am assuming that when I write that. Or I'm allowing the case that, and we do allow that actually, I should be clear. Technically speaking, this is a one-dimensional case, so we start to adopt this convention that ds dt could be negative here with what understanding? That distance in the clockwise direction being developed is counted as negative distance, whereas distance, arc length, being developed in the counterclockwise direction is counted as positive distance. We do make that convention, I should warn you. So like this categorical speed is the magnitude of velocity, therefore it's positive, or we should say non-negative. We lose that. It's a one-dimensional problem. We use the plus minus sign for clockwise versus counterclockwise. I should say plus goes with counterclockwise, minus goes with counterclockwise. Turn that around. Counterclockwise is positive. I'm going to stop talking while I'm ahead. So, but I'm just saying, You could either understand this from differentiating that or from this larger discussion we had, right? What happens if you differentiate again? Now, let me just stop for a second here. That says that the tangential velocity is equal to r times omega. What's the tangential velocity? In my previous lingo, it was v theta, right? V theta is the tangential velocity because it's tangent to the circle over here. And again, omega is the, what is it? No? Omega is the, what? The angular velocity, right? What are the units of angular velocity? No. Radians per second. Technically, the radian's not a unit. It's a dimensionless quantity. But you do need to write it. Otherwise, we don't know you're using radians. So, what happens if we differentiate again? dv dt, right, is equal to d dt of r omega, which is what? R times d omega dt. By the way, that's where it gets interesting if you continue the discussion we were having over here. If you study the relation between linear accelerations and like the accelerations of the polar coordinate formulas, that's where it gets more interesting. But we won't for now, anyway. So what is this? Well, this says that the tangential acceleration, which we've talked about before, remember? Remember I explained to you if we're going along a circle, we can decompose the acceleration into a centripetal piece and a tangential piece. This is that same tangential piece, all right? Then the tangential acceleration is equal to what? It's equal to r times alpha, where alpha is by definition d omega dt. This is the angular acceleration. What are the units for angular acceleration? Radians per second squared. Yeah. I don't want to be a jerk, so I'll stop there. Let's see here. Aha. Ha. Well, I thought it was funny. Let's see here. So, excuse me. These are the relations, right, between arc length and angle, between linear velocity and angular velocity, between tangential acceleration and angular acceleration. It's the bridge between worlds. All right, yes, sir.
Delta S, that change in arc length,
Yep.
so then is regular S the circumference?
Well, it depends on what theta is. I mean, if theta goes from 0 to 2 pi, then S would be the circumference. S is just arc length.
So then what's the difference between S and delta S?
Notation. I mean, whether I want to use theta or delta theta. I mean, I guess you could go over here and you could say, this says that delta S delta t, right, is equal to r times delta theta delta t, and take delta t going to 0, and then that would have given you that. But I think you guys feel better about your life when I just write S is equal to r theta and I say differentiate it. Because when I write the other thing, it's getting dangerously close to writing a limit. And I know no quicker way of sowing discontent in the heart of a sophomore engineering student than to bring up the unpleasant topic of limits. So, I mean, freshmen. You guys are freshmen, right? Seniors? Seniors? No. Okay. Yes.
Over there, you boxed out alpha.
Definition. Yeah. I'm just doing some name calling. I'm saying alpha is the angular acceleration. Now, if you carefully continue this discussion or do it in 3 dimensions, you can derive Coriolis effect and other things that are interesting. Okay, so what's the first thing we did this semester once we got through vectors and started thinking about physics, kinematics? What did we do? Remember constant acceleration, right? What's that? Free fall. Yeah, this is, but that would be constant acceleration a being minus g, right? So it's, I mean, that's a constant acceleration problem, right? So one-dimensional constant acceleration. And so that's what we'll do here for just a second. So if alpha is equal to alpha naught, a constant, right? Then what? You've got what? You've got d omega dt is equal to alpha naught. Guess what? Integrate. What does it give you? We integrate, we get omega f is equal to omega naught plus alpha naught times, tf minus t naught. Oh, why don't I just set t naught equal to 0 for a second here so you guys won't be. So there, I'm assuming, of course, integrating from time 0 to time integrating from t equals to 0 to time t. Right. So there's the final angular velocity in terms of the initial angular velocity. And what if you want the theta? Well, you know that d theta dt, right, is equal to omega. So if I integrate this again from time 0 to time t, what do I get? I get the final theta is equal to the initial theta plus integrating that gives me omega naught t plus 1/2 alpha naught t squared. Look familiar? I hope it looks a little familiar. And what else do we want? We started this game. What are the other formulas? The timeless equation, right? So I'll transform these by analogy. Vf squared equals to v naught squared plus 2a delta x. That translates into omega f squared equals to omega naught squared plus 2 alpha, change in theta. You also have the v average equals v average formula. That translates into the average omega is equal to omega naught plus omega f over 2. The average omega, by the way, is defined to be change in theta over change in t, just the same. That's the average angular velocity, change in theta divided by change in time that you're interested in. Are there any other formulas we knew from kinematics, constant acceleration problem? I mean, those are the big ones. I think everything else is just details, yeah? What's that? The one without acceleration. Ah, I suppose that's implicit within right here. I mean, of course, that's also true. So if alpha naught equals to 0, right? Well, another way. If the acceleration is equal to 0, then what? Change in x is just equal to v times change in t, right? If the angular acceleration is equal to 0, then the change in theta is, yes, just equal to omega times the change in t. But that's a very special case, right? When the angular acceleration is 0. Constant angular speed. All right, let's work an example, okay? Superman shoots his laser eyes at this wheel, and it gives it initial velocity v naught equals to, let's say, 100 meters per second. All right? It rolls without slipping until it stops at distance d equals to 1,000 meters away. Assuming that the motion was constant acceleration, find the angular acceleration of the wheel. To be more descriptive, the angular deceleration of the wheel. Also find the total arc length. Well, I should say find the total angle that the wheel rotated through, right? So how's that work? What does rolling without slipping tell us about the relation between the spinning of the wheel? So like, as the wheel rolls, suppose it rolls through one complete cycle to go from here to here. How far is that? It's the circumference, right? If it rolls without slipping, the distance it goes along the plane is the arc length along the wheel. In other words, the distance is equal to s is equal to r theta. I'm going to say that theta is equal to 0 at the starting point, just to keep things simple, okay? So, I mean, this is the final theta, right? Since I said d was 1,000 meters. So what's the arc length subtended? Oh, okay, so you guys choose the radius. What do you want the radius of this wheel to be? Radius equals 1 meter. Thanks. That's gonna help this problem have a lot of. Let's make it 2 meters. At least it feels like we're doing something. All right, so 2 meters. So you get 500 radians. Ooh, I wonder if this even makes sense unless I give a time. I said it's constant acceleration, right? And I said that it's at rest over here. Is that enough information? Well, it has constant deceleration until it stops. I mean, what's that? I asked, yeah, what are we stopping? I said it in words, I didn't write it. My question was, what is the deceleration? What is alpha? Assuming it's constant. Yeah, I think we do, because we have what? Omega f squared equals omega naught squared plus 2a. So we can use a timeless equation, basically, right? So omega f squared equals omega naught squared plus 2 alpha change in theta. We don't know alpha, but we know everything else here. So alpha is equal to omega f squared minus omega naught squared divided by twice the change in theta. What's that give us? So I get minus 100 meters per second quantity squared divided by 2 times. Oh, I'm an idiot. Oh, no. Excuse me. Don't believe that. No. What is omega naught? Right, omega naught should be what? It should be v naught divided by r. Right? If you want the radians per second, you must take the meters per second and divide by the radius. Or in other words, if you go back to this, put a knot on it. solve for omega naught, divide by r, okay? So omega naught is v naught over r, which is in our case 100 meters per second divided by 2 meters. See, don't you feel better about my decision to make that 2 meters? Otherwise, this would have all seemed so... What's that? That is a... Well, I mean, Superman. Superman can shoot his laser eyes and make a 2-meter ball roll 1,000 meters. It's no big deal, right? I'm sorry, is that a spoiler alert? I haven't seen the...
Beat Batman?
Is he going to beat Batman? In terms of the weight of his fictional legacy, the answer is clearly yes. Because, I mean, I'm saying about Batman. I mean, Batman obviously has the better story. I mean, Superman's like supposed to be stronger than everybody else. Then why does he have difficulty beating anybody? I don't know. It's always... Oh, kryptonite. That's just such a weak excuse. Like, I don't know. I don't like Superman.
I feel like this tactic could be treated by Aquaman.
Aquaman? So you got 50 radians squared divided by 1,000 radians. You're left with 1 radian and 1 second squared dividing, which makes sense. You want a radian per second squared for your units of angular acceleration. What does this work out to? Say again? There you go. That's the constant angular acceleration which is necessary for the wheel to stop. Es bueno? Yeah. Let me see if I have any other nice problems to show you. Here, let me show you this. Let me show you an example with numbers. This is from lecture 25, example 2. Let's hit half the lights in here. Could you guys kill half of the lights? Thank you. So here we have a car accelerates from rest to 40 meters per second using wheels with a 40 centimeter diameter. If the linear acceleration was constant and took 5 seconds, then find the angular velocity and acceleration of the wheels. How many revolutions do the wheels make? Okay. Yeah, so that's the other fun thing, is we like to think about revolutions as another measure, another description of angular displacement, right? You can talk about radians or you can talk about revolutions. What's the connection? How many revolutions do you get? For 1 revolution, how many radians? 2 pi, right? So if I have like 4 pi radians, that corresponds to 2 revolutions and so forth, right? So the relation between the linear and angular velocity is v is equal to omega r. So my r is 40 centimeters divided by 2. Notice that I have annoyingly described the problem in terms of diameter, which is useless. Radius is where it's at. So 0.2 meters, and obviously the initial angular velocity was 0, and because it accelerates from rest in this case, unlike the problem I just covered up, we start from rest and then we're spinning as you go on. The final angular velocity would be 40 meters per second divided by the radius, right? That's the linear velocity divided by the radius. Gives me 200 radians per second. And from that, I can calculate the angular acceleration because it's the final minus the initial divided by time. I think that might have been the question. Yeah, that might have been the formula you're talking about. Maybe. I've written that here. But if you solve this for alpha, you get that. Like solve that equation for alpha, that's this equation. Like instead of I have omega f equals omega naught plus alpha t. Well, if you solve that for alpha, you get alpha naught is equal to omega f minus omega naught over t. Anyway, all this is saying is that in the case of constant alpha, constant angular acceleration. The constant angular acceleration is simply the change in angular velocity divided by the change in time. Not especially surprising, really. So 200 radians per second divided by 5 seconds, because that was how much time. And so I get 40 radians per second squared. It follows then that the angular velocity as a function of time is just 40 radians per second times t. And I can also figure out theta by integrating that. I get theta naught plus 20 radians per second squared times t squared. And so I get a net of weird. Of course, I planned it. No, I didn't plan it. That's what makes it so weird. Cool. Sorry. I rejoice in the little things like this. But anyway, that's 79.58 revolutions. So, yay. Let's talk about rotational kinetic energy. I'm glad I have this open because I didn't want to write this picture out. I wanted to just talk about it with you. If I have a finite number of particles, all right, and they're all basically, imagine them like, think about a Christmas tree is a good example. Take a Christmas tree that's really rigid and put ornaments that are not hanging, but they're like glued onto the branches, all right? So, and then you're rotating the Christmas tree around its axis, right? The question is, what's the kinetic energy of the Christmas tree? And suppose the Christmas tree is infinitely light too, and all you care about is the mass of the ornaments, right? Then the question is what's the kinetic energy of such a rotating system? So all of the masses are somehow rigidly affixed a certain distance from the rotation axis, right? And it's rotating around that axis. The question is, what's the kinetic energy of such a system? All the kinetic energy is coming from the masses. There's no mass anywhere else. You know, what's it look like? What's the formula for such a thing? Well, all of the speed for each one of these masses is just in terms of its radial distance from its axis. It's got no velocity that's like this direction. It's all just wrapped up in the radial, the spinning direction, the rotational direction. So when I calculate the kinetic energy for each one of these masses, the 1/2 mj vj squared, I can completely characterize it in terms of the radius, the distance it is from the axis, right? That squared times omega squared. That's what I get. That's how I get a rotational velocity, r omega, right? And on the other hand, we're assuming that these are all rigidly attached to that same apparatus, right? So they're all spinning with the same omega. This is why it's like a rigid body. Like if I spin, this is an example of a rigid body. If I start spinning it like this, you see all points on the markers, they spin at the same, well, let's see here. Maybe a better example would be like this. If I could do this decently. You know, this is an example of a rigid body. If I could spin this at a uniform rate around the center joining point of the two markers, what's the angular velocity of a point on the red marker? What's the angular velocity of a point on the purple marker? What's the angular velocity of a point on the green marker or the black marker? What's the angular velocity? What's the connection between the angular velocity of different points? How many radians per second are the points on the markers not at the pivot point going? They're all going the same angular velocity. That's why this is a rigid body. They don't share the same linear velocity, right? This piece is going much faster than this piece as it spins, right? But they all share the same omega. See that? And so that's why you can pull omega out of this calculation. And then you're just left with 1/2 this thing, omega squared. And that thing we define to be I, the so-called moment of inertia. For a finite system of masses, the moment of inertia is simply the sum, j equals 1 to the number of masses, of the jth mass times the distance from the jth mass to the rotation axis squared. And that's the moment of inertia. That's the rotational analog to mass. And so the rotational kinetic energy is 1/2 I omega squared. If you think back to the derivation I did a little bit earlier today, what did I have there? Remember I had kinetic energy 1/2 m r dot squared, right, plus 1/2 m r squared theta dot squared, right? Look at what that was. See, this is the translational kinetic energy, which we're assuming is 0 in this discussion over there. We're assuming it doesn't move along its distance from the rotation axis is not changing. But this, on the other hand, is exactly I is equal to m r squared. The moment of inertia for a single point mass is simply the mass times the radius squared, where the radius is the distance from where it's rotating to the axis of rotation. All right, fine. What's an example? Let's look at an example here. So suppose you got a barbell. Well, that's not the right thing to say. You have M1 and M2, and here you have axis of rotation. Let's suppose that this distance is R1, this distance is R2, and suppose the thing is spinning with angular velocity omega. What's its kinetic energy? Assuming that the rod which connects the masses has negligible mass. So the kinetic energy of such a system, let me turn on the lights for just a second. So what we do is we say kinetic energy is 1/2 I1 omega squared plus 1/2 I2 omega squared, right? What is the moment of inertia for M1? M1R1 squared, omega squared, yeah. And then 1/2 M2 R2 squared, omega squared, right? And so that would be it. That would be the kinetic energy. Now that's okay, but that's not really that interesting of an example, right? What's much more interesting is if I had something like a ruler. Man, I wish I brought a ruler. Oh, I can make one though. So like this thing, right? If I spin this thing around its center point, what's the kinetic energy of this system? What's the kinetic energy of this set of markers it's spinning together? Yeah. And what if I was instead spinning it like this? What would the rotational kinetic energy of the marker be if I did that? If I was spinning it with the same angular velocity as I was like over here, which one would have more kinetic energy? Like this or like this? Ah! We'll never know. Well, in order to answer those questions, and we don't have enough to answer them yet, we need to understand what's the continuous analog of this. All right, so if you have some if you have some blarb like this, and it's rotating around some central point, right? And if you were to say, here's a little dm, a distance r from the rotational axis, then the moment of inertia for such a thing, so this is all rotating around. There's an axis coming out of the board, guys, like so. And it's rotating like that, all right? What's my symbol for that? What was it? Circle dot, right? Axis, out of board. That was supposed to be board. Sorry about that. Anyway, what's done is done. So some extended body, all right? What's the moment of inertia for an extended body? What you do is you just say, well, the little bit of inertia for that little dm is what? It's just r squared dm. So to find the moment of inertia for the whole thing, we just do integral over the blob of r squared dm. And that is the generic idea of calculating the moment of inertia of some continuous distribution of mass. You just add up the moments of inertia for each constituent point mass that make up the mass. You're like, well, we didn't cover integrals of blarbs yet. Yes, so blarbs, yes. What's a blarb? Don't know. It's a blonde blob? What? No. No. Are blobs blobs blonde? I don't know. Blah blah blah. All right. So, can you turn off the light again? Thanks.
Is there a rotational no on for friction?
Yeah. Don't do that to me today. All right. That's so apparently, this is actually a way of making my last example interesting. But anyway. Oh, see, we have outlived the usefulness of lecture 25. I think we are now in lecture 26. All right. Don't do that to me. All right, so again, here's the general principle. To calculate the total kinetic energy of a blob rotating, you would want 1/2 the moment of inertia times omega squared. Again, it's the motivation for defining moment of inertia that way is that it gives us kinetic energy, all right? And I'm just adding up the kinetic energy of each of the particles making up the blob, and that's where this is coming from. Enough about that. So how about this? The moment of inertia for a rod of mass m, of length L, we're assuming that the mass is uniformly distributed along the rod. So here's a picture. I'm basically looking at like we were doing a second ago, right? This thing, right? And it's rotating. Well, sorry, wrong way. Like this. Okay, you get the idea. And then, so I have to calculate this integral from 0 to L of x squared. And what's this? So dm is what? It's lambda dx. What is lambda? Lambda is the mass per unit length, which, by the way, is the total